that is the carbonyl condensation. So in the last class we discussed whenever you have a carbonyl compound, okay, let's say this acetaldehyde, and you take a base, okay, when in a catalytic amount, then it will make an enolate. Okay, so this was so this is called enolate. So we showed that both enol in acidic condition, enolate in basic condition. Okay. Last chapter we talked about that if you take an electrophile, let's say Rx, generally halogens, so it will react like this. So it will form R, this one, okay? That was all about the last chapter. This chapter talks that carbonyl condensation. If we take a catalytic amount, okay, and there is no electrophile, just the carbonyl compound, then it will react with itself. Some of the molecules will be converted into an enolate, and they will react with the enol form of the remaining molecules. So what will happen? This will come here, and this will react here, and this will go here. Okay. So what will be the product? It will be CH3, CO minus H, CH2, COH. Okay. Two similar molecules, they are combined together. And then from the solvent, it will take a proton, and the base will be regenerated. So it will be CH3COH and the aldehyde. Okay. So what is the product you are seeing? In the product, we have two functional groups. One is from the parent molecule, the aldehyde, and another is the OH. Okay. So the product is an aldol, aldehyde and all alcohol. Okay, aldol. So this is so this reaction is called aldol condensation. Okay. So what happens here? The new C-C bond, new carbon-carbon bond formed here. Okay. So it's actually a carbon-carbon bond formation between the alpha carbon of the aldehyde with the carbon of the aldehyde. Functional group. Okay. So this is this is a very common reaction, widely used. It happens a lot in our body, in our biological system. Okay, and for that, the enzyme is used is aldolase. You guys will study in biochemistry aldolase. So it's two types, type 1 and type 2. So yeah, just read the book. There is a section that explains. It's very nicely explained, and you guys will study more in biochemistry. Okay, so next, this aldol reaction. So now if you have, suppose these two molecules, okay, take acetaldehyde plus propanaldehyde, propanol, okay, and take catalytic amount of sodium hydroxide. So what will happen? Some of these molecules will form an enolate. You see, this can also form an enolate. Okay, under basic condition. So now what can happen? This can react with itself that we saw earlier. Okay. This can also react with this because the mixture. Okay. And this can react with itself, or this can react with this, like this. So when we have different types of molecules, so what we'll see, we'll say mixture of products. Okay, three different types of products. Try to write. Okay, I showed you guys the arrows, so try to write all three products. Take this one as a home assignment. Okay. So next, if we take suppose this benzaldehyde. Okay. And then you take, let's say, propanaldehyde. Propanal, and there's a catalytic amount of base. So what will happen? You see, in this case, this benzaldehyde cannot make enolate. See this one. Benzaldehyde cannot make enolate because there is no hydrogen on the alpha carbon. Okay, so no enolate. So there are so many molecules. If there is no alpha hydrogen, okay, I mean hydrogen on the alpha carbon, then there is no possibility of enolate formation. This can make enolate like this CH3, CH, double bond O minus. Okay. And then here it can react with this, and it will react with this. So here the crossed aldol product formation here, then it is you will not get a lot of mixture of products. So O minus here, it will have hydrogen, and then carbon, hydrogen, and this carbon has CH3, so you can write here CH3. Okay. And this, after accepting proton, it will make OH. So I'm not writing the hydrogen, just CH3, and then aldehyde. Okay, so this is the reaction of two different molecules, aldehyde molecules. Okay. Now, if you do room temperature reaction, okay, the reaction will stop here. If you heat it or treat with an acid, heat or acid, okay. So I'm showing you guys with the heating. So the condition is basic. Do you see? I'm not doing anything. The condition is basic. What will happen? The base will abstract a proton from here as well. Okay. So what it will form? I'm writing the benzene pH in short. So OH, here you will have an aldehyde, H, CH3. Okay. I see. So this is the base. So next step, what will happen? It will come here and OH will leave. So this is the dehydration reaction, elimination of water molecule from the compound. So it will form enol. from enol. Okay, so this is the next step, an aldol product, aldol, and you heat it or under acidic condition, it will form the double bonded product. And now what will be the mechanism under acidic condition? You see this one, the OH can be protonated from the acid if you add the acid in the reaction. So what will happen? pH, I'm showing the different dehydration mechanism, okay, here, and you have hydrogen here. So OH2, here is the water as a leaving group, that is the best leaving group. You can recall chapter 11. So then water molecule will take this proton and this will leave. Okay, so the product will be same dehydrated. Okay, either you heat it or acid treatment, the OH will be gone. And remember, this under basic condition, it is this mechanism is called E1CB mechanism. Okay, elimination unimolecular conjugate base. Okay, so these are the reaction of aldol condensation. So if you take even ketones can undergo aldol condensation. So if you have, let's say this acetophenone, suppose, okay, and you take a base. So what will happen? This O minus will take one of the protons and it will make an enolate. Okay, so enolate will react with another acetophenone molecule. I'm writing the acetophenone, just a little bit simple structure. So what will happen? So I'm writing this pH, PHCO, O minus, and pH. See this one? And then after taking proton from the solvent, it will make the aldol product. Again, if you heat it or you do acid treatment, it can go elimination, say H2SO4, H. So this will leave after protonation. So what will be the product? The product will be okay. So this is these are the aldol reaction. So what is the overall reaction for this? So easy to remember the overall reaction. If you have, let's say this one here, okay, you have a ketone. One molecule will give 2 hydrogens. You have 3. Here, let's say 3. And another, the same will give the carbonyl. Okay. So before the dehydration, okay, if you will write the dehydration, including dehydration, it will be H2O. See, the oxygen and 2 hydrogen will be gone. That is the aldol condensation reaction. So it will make like this, plus H2O. Okay. So this molecule, this reaction, so here so far we talk different molecules. So the reactions are intermolecular, different molecules. Now, if you have, let's say, like this molecule, yeah. How many enolizable hydrogens in this molecule? So adjacent to the carbonyl, see here 3, 2, 2, 3, 10. Okay. So this 10, so you can make, so this is a symmetrical molecule. You can make enolate, see two types of enolate generally like this. One enolate, sorry. One enolate will be this, okay, this side, and another enolate could be from this side. Okay. So because the enolate reacts with another carbonyl compound, so what happens, you have here the carbonyl sitting in that molecule. And always remember, the intramolecular reactions are favored over intermolecular reactions because of the proximity effect, because this carbonyl is very close to this one. Okay. So what happens, see if it reacts here, this and this will come here, what it will form? It will form, you see, this will make bond with this. So what will be the ring size? 1, 2, 3, 4. So you will get like this. O minus, here you have a methyl, and here O, see this 4-membered ring. Okay. Now, if this one reacts, what will be the ring size? Here you see 1, 2, 3, 4, 5, 6. So what will you see? Like this one. See that a bond is forming between 1 and 6. So you need to be careful to put the ketone carbonyl functional group in a proper position. So if it is here, then you will have here O minus and you'll have CH3 here. Okay, the bond formation took place between 1, 2, 3, 4, 5, 6. Okay, now here you see one side it is making 4-membered ring, another side it is making 6-membered ring. Okay, so whenever you have an option, because it is extremely strained, so no product formation, this will be the formation. Okay, so remember, whenever you have a choice of the ring size, so 6-membered is the most favorable. And if you have 5-member versus 4-membered or 3-member, then 5-membered is favorable. So based on the stability, the ring formation will take place. So this is the intramolecular aldol condensation. Okay, any question? So this is, so you can write from here, after protonation of the OH, it will make OH, CH3. Okay. Further reaction you can do after heating or acid treatment. Okay. This OH will be gone via E1CB mechanism. So the double bond enol formation can take place. Okay, the similar reaction can happen with, so these are the aldehyde ketones. Similar reaction can happen with esters as well, okay, because esters also have carbonyl functional group. So see this one here. If you have ethyl acetate, let's say the very simple example, ethyl acetate. Here you need to keep in mind that you need to have a base of this similar size, otherwise you will get different product. So if you take sodium ethoxide, okay, sodium ethoxide, later I will short I will write NaOET, okay. So what will happen, this will take a proton here, one of the protons. So what it will form, it will form the enolate. Again here O minus OET. Okay, enolate. This can react with the another ester molecule. So what will happen? It can come here, it can go here, and this will go here. Huh? So what will happen? CH3CO minus OET CH2CO OET. Okay, so if you guys can recall from the previous chapter, nucleophilic acyl substitution, for a sp3 hybridized carbon like this one, okay, if you have O minus and another oxygen, then the another oxygen will leave, so it will come back, this will leave. So it's a nucleophilic acyl substitution. Okay, so what will be the product? The product will be CH3 OCH2 COOET. Okay, nucleophilic acyl substitution. So chapter 22, 21. Okay. So this will be the product. So it is the first two step enolate formation and then addition, same as aldol condensation, but the next step is the kind of acyl substitution that OET leaves. So this will be the product. This reaction, just different name, is called Claisen condensation. Okay, Claisen condensation. Okay, so this Claisen condensation, again, we can show it as intramolecular. This was the intermolecular. We can show as intramolecular. So let's say if you have OET, this ester, okay, diester, 2, 4, 6, 7. Yeah. So here you don't have like previous, you have only one option to make the enolate type. Either you take this hydrogen or take this hydrogen or this hydrogen. So this is the thing, this is. So enolate formation. And either side you make, it will be the same. So enolate, here O minus OET. Okay, this will come back and this will react, this will go here. Okay, so here again you need to be careful to make the ring size. See, suppose if you do the numbering, this carbon 1, 2, 3, 4, 5, 6, 7. So the new carbon-carbon bond formation is taking place between 2 and 7. Let's see this. 2 and 7. So what will happen? So 2, 7, 2 to 7 means 6 carbon, 6 carbon means 6 member ring. So now see here 2, suppose this is 2. So what will have at 2? 2 at 2 you will have the ester functional group outside. Okay. So 1, 2, 3, 4, 5, 6, 7. At 7, you will have the O minus NOET. Okay. So now this will come back and this will leave. So you will get the product here. Okay. So this is the intramolecular Claisen condensation. Okay. This is also called the Dieckmann reaction. Okay, so this is the reaction. So now, when you remember, see what is this look like? Previous chapter, do you guys remember what is this one? This substrate look like? This looks like acetoacetic ester. You know, this here you have the ketone. So here the hydrogen is very reactive because it is flanked by 2 carbonyl groups. So these are the different reactions. Right? So like this, I'll give you guys another example. If you have, let's say here, cyclohexanone, okay? And you take an active methylene compound. What is that one active methylene compound? You take malonate or anything, okay? So here, OET, acetoacetate. Under basic conditions, sodium ethoxide, what it will form? What it will take, see this hydrogen is these hydrogens are strong acidic, okay, because of the carbon. So here it quickly will take this proton. So here you will have the negative charge. This will react with this. Okay. So what will be the product? The product will be like this. So here you will have O minus, and here you have CH3 OET. Okay, so here then it will take a proton, it will be an OH, and this here you have one more hydrogen. You see this one? So this is because a catalytic amount, it will be regenerated, and the base will take again this proton, and this will be protonated. So what will happen? OH, here you have a negative charge on carbon, and this carbon has acetyl group as well as, OET. Okay, so now this as a conjugate base like E1CB mechanism, this will be gone. So the product will be like this. Okay. So what is the overall reaction? See the overall reaction, see this active hydrogens 2 and oxygen is gone in the form of H2O, and the result is the formation of the double bond. Okay. So these are the condensation reaction. I'll give you guys an example that is related to my research. Once I used to do work on this. See, if you have these are very interesting molecule. So it's kind of little bit big. Okay, so don't go to the structure. Just concentrate on the reaction. So here you have the aldehyde functional group. Okay. We took an active methylene compound. So what is that? That was little bit active methylene. This cyanoacetic acid. What is this molecule? Cyanoacetic acid. See here in the last lecture, I told you guys that the cyano group can also make a good active methylene compound because of the stabilization of the anion. So we used to take a piperidine base. Okay, this is the base. So what will happen? The base will take this proton, this will react here. Okay. And then after the conjugate base and then elimination, the product formation will be like this. You see this one? So overall, just like the last reaction here, H2 and O is gone in the form of water. So this molecule is called cyanosinamate. See, this is the cinnamate, like this structure is found in spices, cinnamon stick. That's why it's called cinnamate. So cyanosinamate. So these molecules are very good anti-cancer agent, and they work on the monocarboxylate transporter. So it's a different one. You guys will study some higher biochemistry, molecular biology will hear about this. Called monocarboxylate transporter inhibitor, and they are very potent against solid tumors. So because this protein MCT is highly overexpressed on solid tumors. Okay, so these are the overall reactions with the carbon-carbon bond formation with the active methylene compounds and the carbonyl carbon. Okay. Another reaction that is particularly active methylene compounds, they like say this one here. I showed you guys this cyclic structure formation is starting from here to here. You see? So now we will start from there. So this molecule if you react this molecule with methyl vinyl ketone, okay, this is methyl as a ketone, and you have an alpha beta unsaturated double bond. Under a basic condition, so what will happen? Sodium OET. So what it will do? it will quickly take this proton, active methylene compound. Okay, so here it will go and it will form the nucleophile, and this is a soft nucleophile. What is soft nucleophile? If you guys remember the Gilman's reagent type. Okay. So what happens? This one undergoes the reaction here, and this will go here. This will go here. Okay. So what will be the product? So the product will be so O minus and here CH2. That's an enolate. Okay. And after workup with an acid, or just this enolate will take a proton from the solvent or the conjugate acid. So what will happen? The base will be regenerated. So the product will be like this. OH like this one here. You see here, this is one carbon. So 1, 2, 3, 4 carbons. Okay. Now this one ketoenol tautomerism, what it will make? It will make a ketone. So the ketone will be like this. Okay. And because it's a basic condition, see here. Now this the base sodium ethoxide. Here you have 3 hydrogens. I'm writing 1 hydrogen. So this can take this proton, and this anion can react with this. Okay. So what it will form? See the ring size: 1, 2, 3, 4, 5, 6. 6 carbon ring formation. So you have already one 6 carbon ring. So it will be like this, and here you will have O minus, and this will be 6. Okay. See the same repetition. So it will take the proton here, the base. It will take the proton from the conjugate acid. Okay. And then the base will take proton from here. This will come here, and this will leave. E1CB mechanism again. So what will be the product? The product will be like this. Okay, these are many steps, but the repetition of the steps slightly different, and it gives the different products. Okay, so remember here, this is the different ones. Okay, so they make the cyclic structure. So this reaction from here to here, see, This is the reaction from here to here after keto-enol tautomerism. It's called Michael addition. Michael addition. Okay. And from the Michael addition followed by intramolecular cyclization, aldol reaction. What is this one? Intramolecular aldol reaction from here, and then removal of water, so aldol condensation. So Michael addition followed by aldol condensation, intramolecular aldol condensation, both together is called Robinson annulation. Okay, Robinson's annulation. Annulation means ring formation, the ring formation here. Okay, I will give you guys one more example. Let us say, let's take a simple example, the acetoacetic ester. Okay, here. Okay, ethyl acetoacetate. What will happen if you take a base, sodium ethoxide, and you take an alpha beta unsaturated ketone? So this is called methyl vinyl ketone. Generally methyl, and this side vinyl ketone. So what will happen here? You have active hydrogens. The base will take this hydrogen, and the anion will undergo Michael addition. Okay. So what it will form? It will form like this. After keto-enol tautomerism, this will be okay. So the base you have here will take another this hydrogen, okay, sodium OET, the base will take this, and this will go intramolecular aldol type reaction. And always remember it, for Robinson annulation, the ring size will be 6-membered. So you will have like this. So here O minus, and you have CH3 here, and this carbon has ethoxy formate, and here you will have the ketone. See, if I'll give numbering here, 1, 2, 3, 4, 5, 6. So this will be 1, 2, 3, 4, 5, 6. Okay. So again, this will be from the solvent or the conjugate acid. The OH will be protonated. It will make OH and CH3. Here you will have OET, and then so next step, the base again will take this hydrogen for E1CV type mechanism to remove the water molecule, and it will make a 6-membered ring. Okay. Okay, so this will be the product formation. So this is the Robinson annulation. Okay, this Michael addition is also useful to make Michael addition with the enamines. Chapter 18, okay, enamines. 18 and 19, enamines. What are enamines? So I will show you guys the enamine mechanism again, enamine. Don't forget this one. So if you have a ketone, okay, and you react with a secondary amine, let's say this, I'm writing this cyclic amine, okay. So what will happen? This will be like this. So after proton exchange, this will be like this. Okay. So in the reaction condition, this pushes out and this leaves. So this will form positive charge. Okay. So this conjugate base or even the solvent here can take this proton, this will go here, this will go here. So what will form? It will form the enamine. In so why this is called in? In means double bond and amine, the nitrogen. Like enol, in all. Okay. On the double bond OH, here on the double bond amine, enamine. So if you'll see the resonating structure of this one, it is like this. Okay, enamine resonant structure. Positive charge and negative charge. So this carbon is, see if you can compare this one with here to here. So this is the alpha carbon and you have a negative charge. And it's a soft nucleophile, okay? It is just like for the enolate formation, the negative charge. So this one also, so when enamines, if you react enamines with alpha beta unsaturated ketones like this, so what will happen? This will come here and this will undergo Michael addition. Okay, so what will be the product? Product will be like this. And then O minus and CH3. So let me get clearly this. Okay, and with reacting with water, working up with the water, this will react because this carbon is very strong electrophile, and this again can take proton here, this will go here. So what will be the product? The product will be oh sorry, here OH. Okay, so this one here, it will be gone, the deprotonation, and the nitrogen is very basic, it will be protonated. So what will form? This will form here like this. After the protonation of nitrogen, this is the positive charge, and you'll have OH and this. Okay. The next step, suppose just the water molecule can take this proton, this will come here, and this will leave. So the product will be like this. And the plus here, the pyrrolidine will be regenerated. So it's a catalyst. Okay. So what did you see the overall reaction? That this alpha beta unsaturated tone is added to this alpha carbon. Okay, this is the overall reaction. I will give you guys another example. Let's see just if you have acetone. Okay? And you take, let's say, this aldehyde, okay, alpha beta unsaturated aldehyde. And you take a catalyst pyrrolidine. Okay, pyrrolidine. So what will happen? The alpha this hydrogen will be gone, and the product will be okay. So if you'll see the previous mechanism, this part came from via the Michael addition, and this is the acetone. Okay, so these are the reactions